স্যার আপনি লাইভ আছেন এখন।
Okay, great. So we are live for this session. Now, I request you to, place your comments on the comment box if you have any comments or question. Yeah. So if you have any comment or question, you can always put it in the comment box. In the forum, we have already received a bunch of questions. So what I can do is, in the meantime, I can start answering those questions. And if we receive for any more question during the session, then we can always continue with that. Okay, so let us see. We have 1, 2, 3, 4 questions, and let me try to answer those one by one. Arya says, sir, in lecture 4 of week 1, you said that there are 2 vibrational degrees of freedom, and we, in your course of from classical mechanics, learned that there is only 1 vibrational degree of freedom. Kindly clarify as how DOFs from vibration are 2. Okay. So in classical mechanics, we are more concerned about the coordinate, right? So let us try to elaborate this by writing. Just a minute. I hope you can see the whiteboard. So degrees of freedom. All right. So just adjust this. Now, from classical mechanics, what we have learned is that number of independent or total number of independent codes. Or classical mechanics. Yeah, I must agree that when I taught this classical mechanics course, that never occurred in my mind, because that time I was not very familiar with this equipartition theorem. So in classical mechanics, when we talk about degrees of freedom, it is total number of independent coordinates, right? And in classical thermodynamics, it is total number of quadratic term in energy expression. So when we consider this simple 1D oscillator, which is where we have a rigid wall and we have a frictionless platform on which there is a mass m, and it is attached by means of a massless spring of spring constant k. Now, what is the degree of freedom of this? Let's say this is my mean position, m, or rather I would say this is m. Yeah, so this is my mean position, x is equal to 0. Now if I allow this spring, allow this spring mass system to move back and forth. Displacement from this mean position, or rather I would say x is equal to x0. So if it is at one point, it is at this position, then the displacement will be x, or rather the displacement, we can write a coordinate, let's say nu, or sorry, eta. We can use some notation. Yeah, this is, or rather I would rather use small q, maybe. Small q is equal to x minus x0. So this is my x0, not x. This is x0, and this position, let's say this is x. So my displacement is q minus, as q is equal to x minus x0, and this is my degree of freedom. Now, this is the classical mechanics definition of degree of freedom. That is only one independent coordinate is sufficient. But when we write the energy expression for this simple 1D oscillator, what do we get? We get the energy E of vibration is equal to half m x dot square plus half k x square. Now, this is the kinetic energy. This is the potential energy, and both are quadratic in nature. Quadratic in either velocity or coordinate. Now, the potential energy is quadratic in coordinate, that is x. Actually, I should write q dot and q. That will be more, technically correct. Sorry, q dot and q square. Right, this will be more correct to write because I have already defined q, which is the coordinate. So this is my coordinate. Yeah. Now this is a quadratic term in velocity. This is a quadratic term in position, and both will contribute. And according to the thermodynamic definition, this will lead to 2 degrees of freedom. So, and each of that will contribute half kT and half kT. So that means if we have a classical if we have a macroscopic oscillator, 1D oscillator, single oscillator, idealized oscillator, that will contribute half m q dot square in kinetic energy and half k q square of potential energy to the total energy of the system. So that will be the expression for total energy. But if we have a microscopic vibrator that can be treated through classical equipartition theorem, then irrespective of what is the functional form, irrespective of whether it is kinetic energy or potential energy, both will have equal contribution of half kT to the total energy of the system. And please remember, even in even in the mechanical case, when we have a macroscopic vibrator, the averaged value of kinetic energy and potential energy of the oscillator over a complete cycle are equal. So having the same values for the kinetic energy and potential energy, basically this equipartition theorem talks about average number only. It's an overall ensemble average. So there is no no contradiction when we get equal number for kinetic energy and potential energy. Okay, I hope this clears your confusion. Okay, Aryan also has said in Bond's experiment. Yes, I will come to that. How can I find 4 linear DOF of 4 linear atoms? Okay, I'll come to that. Okay, let me first finish the other questions that I have. Okay, so somebody with a very long name that starts with L has 2 questions. Sorry, I cannot really pronounce your name. And that is my drawback totally. So what is the difference between thermal physics and thermodynamics? Okay, so technically speaking, yeah, so thermal physics is little more broad as compared to thermodynamics, because when we talk about thermodynamics, we talk about the classical thermodynamics that starts with first law of thermodynamics. When the entire world is macroscopic, we do not really jump into the microscopic world. Yeah. I mean, the classical way. We do not jump into the microscopic nature of it. And then we get the first law, second law, and basically first law is an energy conservation. Second law is which we will learn later on is actually a which defines the direction of a process. And there is a third law also, which will be covered towards very end of this course, which is actually the limitation of any thermodynamic process. Okay, so all these laws, these are primarily observational laws. We have not started off with thermodynamics, classical thermodynamics as of now. Okay, which please remember, these laws in thermodynamics cannot be proved, which I'll cover in lecture also, that these laws has to be accepted based on numerous experimental observations. So that is thermodynamics. Now, thermal physics as a whole is a slightly, I mean, not slightly, but more broader perspective. It also includes thermodynamics, but it can also include things like kinetic theory, transport phenomena. It can talk about conduction of heat, which we have not covered. It can talk about radiation, which we will have towards the end of this course, and other things also. So that is why I have used thermal physics as the title, not thermodynamics, because thermodynamics is the classical, in a classical manner, it is relatively narrow. Of course, if we talk about statistical mechanics, where the statistical approach to thermodynamics, that also talks about microscopic ensemble, but that's a slightly advanced way of looking. So at the beginners level, the thermodynamics we will be learning very soon. You will get these lectures. I think probably next week or next to next week we'll start getting this. I mean, lecture 31st onwards, you will get the classical thermodynamics lesson, which is totally macroscopic in nature. Okay. The second question: what is the most efficient way to measure compressibility of a liquid oil? I don't know. Frankly, I really do not know what are the real life experimental techniques to measure the compressibility of any liquid. So, I mean, I'm very sorry, but I cannot answer this question. Does temperature have an upper limit? Now, that is a real interesting point. It turns out that there exists an upper limit known as the Planck limit. Okay. Now, what is the Planck limit of temperature? Let me put a line here. Okay. Upper limit, also called the Planck temperature. Now, this is, to begin with, it's a hypothetical concept. So far. Okay. Once again, I am not the right person to talk about it, but whatever little knowledge I have about this, I can share. See, we know that there are interaction strengths. Like we are in this macroscopic world where we see gravity, and then we have electromagnetic forces. Of course, in the microscopic world, in the atomic and molecular world, there are atomic world actually, there are strong force and weak force. These are the four fundamental forces. Now it turns out, don't ask me how, the gravitational force is probably, probably the strongest force. The so-called gravitron particles, which are hypotheticated, those are at present, I mean, there is no direct experimental evidence of this gravitron particles they do exist, but quantum gravity, there is a field by itself. They predict the existence of a gravitron particle. Now, if such particle do exist, there has to be some sort of a frequency and length scale associated with it. Now, there happened to be a Wikipedia page on this called the Planck units. You can look into it. Now, there is a Planck temperature scale also, which is given by Tp is equal to h bar c to the power 5 root over of g divided g kb square. Okay, so Planck temperature Tp is equal to root over of h bar c to the power 5 divided by g kb square, right? Just, yeah, fantastic. So, and this has a value, so g being the gravitational constant, g being the gravitational constant. I do not remember the value offhand, but probably that can also be found in the internet. I don't remember it, the value exactly. This is this actually is associated with and kb, by the way, is this familiar Boltzmann constant. Probably I should write small kb square if that helps. C being the speed of light. Once again, I should write small c intentionally, and h is the Planck's constant, reduced Planck constant. Right. So this the origin of this is, if there exists a gravitational wave, the wavelength of that gravitational wave should be Planck length, which is uh, once again Lp is equal to root h g bar by c cubed, h bar g by c cubed. Okay, and this basically the concept is, this is the Planck length, that is the lowest possible length scale that is possible, the lowest possible length scale in quantum gravity. Now, if this is equal to lambda, then we can write h c bar by lambda is equal to kb t, Tp, this Tp being the corresponding temperature, and this gives you the expression here, and this has a value of 1.4 into 10 to the power 32 Kelvin, roughly. It will be 1.42 something, but yeah, so it's approximately 1.4 into 10 to the power 32. Now, this temperature scale is not achievable, and as far as I understand, even at the time of Big Bang, immediately after Big Bang, the highest temperature that was, I mean, predicted once again, was of the order of 10 to the power 28 Kelvin or something. So this temperature scale is upper limit, which will, and everything in this temperature will be decomposed into gravitron particle if that particle do exist. So this is, as far as I understand, is the concept of upper limit of temperature called the Planck temperature. Okay. So Arya also once again has a question. Sir, in Bond's experiment, we used the quarter plate. Right now, I am answering the question that was already posted in the Google Forms. Whatever is now coming in forum in the chat box of the YouTube link, I'll answer this afterwards. We use the quarter plate. Can you show us actually how does this quarter plate look like? No, I do not have any picture of that. I can try to give you a different perspective of this. Let's say we have a plate, a rod, and 4 plates are placed at 4 different heights in this rod. Each has a span of this angle is equal to pi by 2, and they are basically complementary to each other. What I mean when I say complementary, that means they all together make this 2 pi angle. Yes, I hope you understand. And the 4th one should be at the back, so you won't be able to see it properly. Yeah, so these are these 4. So last drawing is not very good. So yeah, so the last one will be somewhere here. So, right. So these are the 4 plates which are called the quarter plates, and they will be separated by some length L. Right. So this is what I know, and I have never seen a real life picture of this Born experimental setup, so I cannot answer it anymore better. Okay, Arnab Mondal says hectopascal, hecto actually, it should be not hecta, I guess it should be hecto anyway. Hectopascal to Pascal conversion, I confused a little bit. I know 1 hectopascal is 100 pascals, and also hectopascal is 0.01 pascals. No, both cannot be true. I think you are just mixing it up. 1 hectopascal HPA is equal to 100 Pascal. So Pascal, 1 Pascal should be equal to 0.01 hectopascal, and that's it. Okay. So these are two units. I think you are just confusing between this to conversion. 1 hectopascal is 100 pascals is correct, but 1 hectopascal is 0.01 pascal cannot be correct simultaneously, right? So this is where we stand. Okay, so what else? Okay. So Manoj asking, sir, there is no prerequisite for this undergraduate course, but a large part of the derivation requires knowledge of other subject and make a lot of time completely purse the video lecture. Is there any chance that I could get lecture more elaborate and detailed in the derivation part? Okay. See, Manoj, there is no prerequisite. Yes, I agree to that. But please remember that once you are taking this course as an undergraduate student, you need to have, you must have completed the +2 physics and mathematics, right? And of course, you are pursuing a parallel, first year level course in mathematics, at least, if not second year. So you need to know the basic integration and differential calculus, integral and differential calculus. That is, although I do not mention it as an explicit prerequisite, but if you are already at the bachelor's level, let it be a BTech student or a BSc student, you need to know that. And rest, I don't think we are assuming that you know anything more than this. I mean, +2 already covers the +2 physics and mathematics and chemistry already covers some basic concept, and we are building it from there itself. So I do not think anybody should have any problem understanding the mathematics that we are, or derivation that we are doing in the class. Anyway, still, if you have any specific question, you are free to ask in forum. We will try to answer. Okay, so already there are many questions. Arya already asked this. Okay, I have answered your question, that Born experiment. Yash, how can I find the DOF of 4 linear atoms? What do you mean by 4 linear atoms? Can you please explain, Yash? I don't understand. If it is 4, if it's a linear atom of 4 molecules, then probably, or 4, yeah. Oh, acha, acha. 4, I think you are talking about a linear molecule of 4 atoms. Yeah, so that should not be a problem. See, so these are two different questions, and now I am asking another different, answering another question here. So this is, you have one, so you can think of there 4 coupled vibrator. Right. Okay. I should not say that it's not very difficult. It is definitely difficult, but this is the way you can see. There are 4 masses. Let's call it M1, M2, M3, and M4. Right. And there are springs K1, K2, and K3, and they're moving on a straight line. So this is very important, because if they start to bend and all, the problem becomes extremely complicated. We do not know if the solution really do exist. I mean, of course they exist. It's a finite system, but it's unnecessarily complicated. So if we assume that they're moving in harmony, I mean, moving in one straight line, vibrating along one straight line only, then problem becomes simplified, but still it is a lot more complicated than diatomic, but or triatomic molecule, because here it's a system where there will be at least 4 normal modes of vibration. Okay. Now I cannot really, I cannot give you a simple argument to show this, but let me tell you, there will be at least four independent vibrations, and that comes from the theory of small oscillation. Now, if you are interested in this, there is I already gave a course on classical mechanics, which Arya Pandit was also referring to. Now, that course, I have covered this theories of small oscillation in great details. That is already available in NPTEL portal and in YouTube. So you can go through that. But I can in general tell you that this, we have a 4 mass and 3 spring system. There will be a in general, there it will be this system can be represented in certain form by a 4x4 matrix, and it will not be normalized or diagonalized in order to get the final frequency normal modes and all. So there will be at least 4 such degrees of freedom. Now, one of these degree of freedom can be a zero frequency vibration also. That we cannot say a priori unless we solve this problem. But given that there are 4 normal coordinates, normal modes, that means there are 4 normal coordinates. And in given that, assuming that none of these are zero, like none of these are zero frequency modes, there will be at least 4 into, and please remember, each normal mode will contribute, in this case, how many quadratic terms will be contributed? Just a minute, let me think. Each normal mode will contribute 2 quadratic terms, right, because that is the concept of normal mode, right? Oh, if I have one, just let me think, because this has been a long time since I have, what you call, cultured these things. I can be wrong, so better you go back to the lecture of lecture of classical mechanics and reconfirm. But as far as I remember, I'll try to answer this question. So if there are 4 independent normal modes, so that will give you 4, and each will have 2. Right. So each will give you 2. So altogether, 4 into 2, that means 8 degrees of freedom. That means there will be at least 8 vibrational degree of freedom of this particular system. Yeah, but please remember, please understand this. As I have said, I was not prepared for this type of question because it's more into classical mechanics and small oscillations. So I might be wrong. I tried to give you an answer. Cross check. Better to cross check this with my videos of classical mechanics. Yeah. Okay. Okay. Aryan has another question. Sir, in the expression of number of collisions, you have PCDT, which gives us the number of collisions in time dt. When we multiply it with NdV, we get N Tc dV dt, which gives us the total number of collision. Time dt in volume dV. Sir, you then go on to say that we have, let's say, X number of colliding molecules, number of collisions. Try to fair. So in the above expression, compute, we are not computing number of colliding molecule, but the collision itself. Okay. It's a very, very clever point, actually. Okay. Yeah, I understand. So what he tried to say here is, when we write that the number of collisions. Okay, let me actually go to the lecture notes and quickly verify what he says is what he tried to say. It should be in week 2, I guess. Okay. So lecture 0. Just a minute. I hope I understand your concern. Now, C actually double counting of colliding molecules. Right. Acha. PC and DVD. This is lecture 9 you are talking about. Acha. To avoid double counting of colliding molecules. See this N. Okay. So the expression he is talking about is this. So we have a volume dV in which we have number of collisions that is occurring inside the volume dV in time dt. So we write that as PC dt, right? So we write that as PC dt times n dV, and this is collision frequency, right? Right. So this one is the number of collision in time dt, and this is number of molecules in volume dV, right? Now when we have total number of collision, this is in an unit volume we are talking about. Now when we are multiplying this with the and there is a factor of half, that's where he has a question about whether this half factor should be here or not, right? I think this half factor is justified because, okay, so his question exactly is the expression for number of collision gives the total number of. The above expression, we are not computing number of colliding molecules, but the collision itself. Why then there is a need to divide it by 2? No, actually, yeah, that's where the answer is, because we are actually computing the number of colliding molecules itself. Yeah, so right now what we are in, what we are interested in is the total number of molecules that is involved in the process, right? So this is where this half factor is important, because finally what we are looking at is either the molecular flux or a pressure expression, which is once again correlated with the molecular flux. So in order to get to the from the number of collision to the actual number of molecules, we need to have this half factor into consideration. So if you remember, in the very next step, we multiply it by 2, saying that each molecule, each collision will knock out 2 particles. So this half and 2 nicely cancels out, give you only 1. So essentially, we are we have this one as our number of collision and number of molecule at the same time. But in order to compensate for the number of colliding particles and the number of particles that is knocked out, we have to have this half and 2 factors into consideration, because finally we are talking about total number of molecules only. That is for any practical importance, not the number of collision. Achha, Farooq have a question. Good evening, sir. Did your course on classical mechanics first? Okay. Thank you, Farooq. I have done more than 10 online. Okay. Oh, welcome, Farooq. You are really welcome, and I'm really glad to know that you like my course on classical mechanics. Yeah, the Ariane asking, sir, please save this live session. This will be done by NPTEL team. I have no role to play. I hope it will be saved. You can talk to them. Okay. Ornab Mondal says, no, sir, just like kilometer to M conversion, 1 kilometer is 1000 meters and kilometer is equal to M by 1000, is not it? So if 1 hectopascal is 100 Pascal, then hectopascal is 0.01 Pascal. You also write this in your note. Is not both are true? If I have written this in my note, you just point it, you tell me which one I have this, then probably I have to change one of this. Okay. So you tell me which number I have it, just write it in the comment. Huh? Then I'll try to find out if there is a revised correction needed, then I'll do that. This both of them cannot be. Maybe I have written it somewhere by mistake. One of them has to be not correct. Okay. Anyway, let me confirm the definition of hectopascal. Hectopascal is, just a minute. 1 hectopascal is 100 Pascal. 1 hectopascal is 100 Pascal. So that is correct. Once again, where is it? Yeah, 1 hectopascal is 100 Pascal. This is correct. And 1 Pascal, in this case, 1 Pascal has to be 0.01 hectopascal. Okay, so if I have written somewhere that what was it? If I have written that 1 Pascal, hectopascal is 0.01 Pascal, then it must be wrong. Okay. Yes, exactly. I'm asking this sort of, where did I write this? In which lecture note? Just give me the number of the lecture note. Where did I write this? I'll look into it. Most likely there is a correction. Collision. Okay, Aryan is asking, but sir, PCDT NDV gives you the total number of collision, but not the total number of colliding molecules. Then why did not get it? So this is fine. Just a minute, Aryan. I'll come back to you. Okay. In between, Yash has a question. Sir, I have done your course on classical mechanics, Newtonian to Lagrangian. Will there be a part 2 of this course? No, not as of now. I have no plan to offer another course. And please try to, all of you, please try to keep this discussion down to this thermal physics only. Classical mechanics is another course which is already over. So we are discussing thermal physics. Okay. Yeah, Arnab says, sir, but both should be true, I think, because if 1 kilometer is 1000 meter, and also if you convert 500 meter to kilometer, yeah, 500 meters should be 500 by 1000, then should be, yes, exactly. So 500 meters is 0.5 kilometers. I don't see any problem here. What are you trying to tell me? If 1 hectopascal is 100 Pascal, then are you talking about conversion? I don't know. Anyway, so let's say, let's look at it this way. We have 1 hectopascal is equal to 100 Pascal. So if I have a pressure of 5 hectopascal, I'll just give you some examples if that helps. 5 hectopascal, that will be 500 Pascal. And if I give you a value of, let's say, 100 hectopascal, or let's say if I give you a value of 100 Pascal, or let's say, sorry, if I give you a value of 2000 Pascal, what will be that? What will that be? In order to get 2000 Pascals is equal to how many hectopascals? What will you do? Just think. You will divide this by 100, is not it? So you will get 200 hectopascal. So these are the two examples I have given you. And if I have written anything, I mean, if anything is outside this conversion, if anything of this is not right, you let me. Okay, back to Aryan. But sir, did not convert it. PCDT and DV gives us the total number of collision, but not the total number of colliding molecules. See, each collision will have to have two molecules. That is understandable, right? Because if we have to have one collision, that will include two molecules. Physically, that is the picture. So we have to stay with this. We cannot really go away from. So that means whatever is the number of collision, if I try to track the number of particles, if I have in a container, if I have some molecules and I count that there are altogether 100 collisions that has been taken place over a certain period of time, let's say. So then I can readily conclude that if there are 100 collisions, there has to be at least 200 particles, right? So sorry, sorry. One collision needs two particles, right? There has to be at least 200 particles, right? So that is where we have to put this. No, do I make sense? Just a minute. It gives us a total number of collision and not the total number of colliding molecules. Then why? Total number of collisions. So one collision has to have two particles. Let me go back to this expression once again. Collision in time dt, right? So each collision, okay, let me just go back to my notes and try to see to avoid double counting of colliding molecules. If I have two collisions or one collision, I need to have two molecules at least. If I have 10 collision, I need to have 20 molecules, right? Okay, I'll think about it. I think there is a confusion between this half and this two. Now, where this half should go and where this two should go, I will talk about it. I'll just discuss about it and I'll try to answer this question in the forum. I'll keep this in mind. Right now, I think it is right, but I really cannot explain. So that is my shortcoming. I'll think about it a little more and I'll let you. Okay, so let us wait for. Yeah, of course, Josh, there will be more live session. There will be two more live session of this course, and I would really like you all to participate in this. Okay, so in the meantime, I hope I tried to explain all this as much as I can. For Aryan's question, I'll think about it, about, as I said, about this half and two factor, and I'll write this in the forum, answer this in the forum. And yeah, that's it. So if you have any further question, you may ask. Otherwise, we can call it a day.
So, shall I end the session, sir?
Let us wait for another 1 minute. Maybe somebody still have some question in mind.
Okay. Okay.
Yeah. So, so let me tell you that there will be 2 more live session. The dates of those will be communicated to you through the NPTEL portal, right? So in each live session, for example, this week we are discussing maybe up to lecture week 3 lecture, and the next live session we will be discussing whatever course material you have received so far. You can always ask question from there. And I don't know if you have already started answering the questions, answering the assignments. If you find any difficulty in answering those, you can always ask in the forum. And otherwise, if you have some doubts, like we have discussed today, you can always give you, I can try to answer this question in the live session. Yeah, Zash says, when two gases mix from a mixture, which property remains constant? Okay, I mean, it depends on the situation. If the gases were already at constant temperature, so the temperature will not change. Or like to calculate CPCV or R of the mix. What is R? I don't know. R is, if you are talking about universal gas constant, then it is anyway constant. I mean, it does not matter whether you measure it on a gas assembly or you measure it on this. Entropy changes. Okay, if the two gases were, before mixing, they were already at mechanical equilibrium, then the pressure remains constant. And that's it. So typically temperature and pressure remains constant. Volume definitely changes when two gases mix. Their effective volume, the spread definitely has to change. Otherwise, it will not work. So I guess how to like to calculate CPCV or R. So there are, I think, relations available. I don't remember it offhand, how to compute CP and CV for a gas mixture. Yeah. But if you have any specific question towards this, you can ask in the forum which particular expression you are looking for. If it is available, I will let you know. I'll try to answer that. Either myself or my TAs will answer this question. Okay, so let us, yeah, like I have question in the assignment 1 question 8 where there is a mix of diatomic and triatomic gas. Okay, let me just go to the question. Probably you will, I'll just open this. Week 1. Question 8. Calculate the ratio of specific heat gamma for a mixture of 1 mole of an ideal diatomic gas and 1 mole of ideal linear triatomic gas, right? So let me see the solution also. I think there is a relation available. Right. Okay. Yeah, so there is a, there is a relation actually which talks about what happens when two gases mix, what is the degree of freedom. That is available in one of the textbooks. Which one? I do not remember. So please ask this question in the forum. We will try to answer this. Okay, Dinesh is asking what happens when the gas reacts. Does temperature and pressure remains constant? No. not really. So that is a different question altogether. You have to wait till lecture number 50 to have an idea what happens in a chemical reaction. Of course, this is not a course of chemical thermodynamics, so we will not go into the details of chemical reaction, but we will have an idea. So that is something totally different. So temperature, pressure, everything can change. One thing that is so there is a very different dynamics altogether. So we have to wait for that. Our assignments and notes are sufficient for final exam? Definitely not. You have to study at least one standard text. So I have already referred the books, Garg, Bansal, and Ghosh. I have this book. No, I don't have it right now on my table, but this is a very good book. Yeah, so you can ask, read that or any other standard text that is listed for this course. So just please do not concentrate only on assignments and notes. That is not sufficient. Okay. Okay, so let us close this live session. The time is up for today. We will meet again once again for the next live session. Thank you.
Thank you, sir. I am ending the session, sir.
Yeah, please.